What if everything you've been taught about the beginning of the universe is wrong? I mean, fundamentally, catastrophically wrong. A Nobel Prize winning physicist just made a statement that's sending shockwaves through the scientific community. He said, and I quote, "It's a different universe than we thought." Those aren't the words of someone being poetic. Those are the words of someone who's staring at evidence that's rewriting the rulebook we've been using for decades. The James Webb Space Telescope has been peering into the cosmic darkness, and what it's finding is absolutely terrifying the scientific establishment. Galaxies where they shouldn't exist. Stars billions of years old appearing in regions we thought were too young for such things. And the implications? They're so profound that they're forcing us to ask a question we've been avoiding. What if our entire timeline of the universe is off by billions of years? Stay with me, because by the end of this video, you're going to understand why this discovery matters, not just to astronomers in their labs, but to you, to your understanding of reality itself. This isn't abstract cosmology anymore. This is about reframing everything. But before we dive into the abyss, I need you to do something for me. If you're watching this and you're still on the fence about this channel, hit that subscribe button right now. The algorithm isn't friendly to educational content, and your subscription is literally the only thing that keeps this research and production alive. It takes 1 second, and it helps us reach more people with this mind-bending information. And here's my question for you. Where are you watching this from? Drop your country in the comments below. I'm genuinely curious about our global community. We've got viewers from over 140 countries, and I want to shout out where this conversation is happening. Also, what time is it where you are? I'm asking because the universe doesn't care about time zones, but I do care about who's joining this journey with us. Now, let's talk about what got a Nobel Prize winner so worried. For the last 100 years, we've had this beautiful story about our universe, the Big Bang Theory. It's elegant, it's relatively simple, and it's been confirmed by observation after observation. The story goes like this. About 13.8 billion years ago, everything, and I mean literally, everything, all the matter, all the energy, all of space and time itself was compressed into an infinitely dense point. Then, boom, the universe began expanding. We've tested this theory with the cosmic microwave background radiation. We've measured it with the Hubble Space Telescope. It all checked out. Think of it like this. Imagine a balloon covered in dots. As you blow air into the balloon, every dot moves away from every other dot. That's what's happening to galaxies. Space itself is expanding, carrying them apart. It's been the cornerstone of modern cosmology for decades. Here's what's crucial to understand. Timing is everything in this story. If we know how fast the universe is expanding, something we call the Hubble constant, we can work backward to figure out exactly how old everything is. It's like having a video of the universe being created, and you're rewinding it to find the beginning. In the 1990s, astronomers discovered something that earned them a Nobel Prize. The universe isn't just expanding, it's expanding faster and faster. There's something called dark energy, making up about 68% of the entire universe, pushing everything apart with increasing force. The physicist who discovered this was Saul Perlmutter, along with Adam Rees and Brian Schmidt. Their 1998 discovery won the Nobel Prize in Physics in 2011, and it fundamentally changed how we think about the cosmos. But here's where it gets interesting. For the past 30 years, we've been refining our measurements, getting better equipment. The Hubble Space Telescope gave us better data. And then, in 2021, the James Webb Space Telescope launched. It's the most powerful space telescope humanity has ever built, roughly 100 times more sensitive than Hubble. And immediately, and I mean immediately, it started finding things that didn't fit the timeline. What if I told you that the very first galaxies we could detect appear too large, too developed, too mature for the amount of time that should have passed since the Big Bang? Think of it like this. Imagine I tell you the universe is only 13.8 billion years old. That's the age we're working with. But then you find a 65-year-old human in that universe. The math doesn't work. Something's wrong. In March 2024, a study published in the Astrophysical Journal by Lab et al. Found galaxies that appear to be 13.5 billion years old in a universe that's only supposed to be 13.8 billion years old. That gives the universe only 300 million years to go from nothing to massive, fully formed galaxies. For perspective, 300 million years is less time than it took Earth to go from single-celled organisms to complex life. And here's the mind-blown moment number one. The galaxies James Webb is detecting are also heavier than they should be. They contain too much mass for their apparent age. This isn't a small discrepancy. This is off by a factor of 10 to 100 times too heavy. The scientific community's response? Denial followed by scrambling. Because if these observations are correct, and the evidence is mounting that they are, it means one of our fundamental assumptions is wrong. Either 1. The universe is much older than 13.8 billion years. Or 2. The early universe operated under different physical laws than we thought. Or 3. Our models of how galaxies form are completely incorrect. None of these options is comfortable. None of them fits neatly into the framework we've built over the last century. And this is exactly what that Nobel Prize winner meant when he said, "It's a different universe." Now, before we go deeper, let me pause here because this is important. If you're enjoying this so far, if your mind is getting that tingly feeling of confronting something that doesn't quite fit, that means you're thinking critically. And I want to encourage that by asking you to engage with this. What's your intuition telling you? Does the universe feel older to you? I know that's a weird question, but drop your thoughts in the comments. Let's build this understanding together. Here's the thing about measuring the universe. It's absurdly difficult. We can't exactly send a measuring tape from Earth to a distant galaxy. So astronomers built something called the Cosmic Distance Ladder. It's a series of overlapping techniques, each building on the previous one, each introducing its own potential for error. The foundation of this ladder is parallax. It's simple geometry, really. You know how when you hold your finger up, can close one eye, then the other, your finger appears to move? That shift is called parallax. Astronomers use the same principle. They measure where a nearby star appears against distant background stars from opposite sides of Earth's orbit around the Sun. The shift tells them the distance. This works great for nearby stars. But for distant galaxies, we need the next rung on the ladder. That's where Cepheid variables come in. These are stars that pulse. They get brighter and dimmer in a regular pattern. In 1908, Henrietta Leavitt made one of the most important discoveries in astronomy. She noticed something incredible. The period of pulsation, how long it takes for a Cepheid variable to complete one cycle, directly correlates with its actual brightness. That means if you measure how bright it appears to us and how fast it's pulsing, you can calculate exactly how far away it is. This discovery was revolutionary. It gave us our first way to measure distances to other galaxies. And it all traces back to one woman, Henrietta Leavitt, whose groundbreaking work in 1908 literally gave us the cosmic distance scale we still use today. Think of it like this. Imagine you're on a dark road and someone holds up a flashlight. If it's exactly the same brightness as a flashlight, you can estimate the distance based on how bright it appears. Cepheid variables are cosmic flashlights with known true brightness. The problem? The farther away we look, the more rungs we add to this ladder. And each rung is an opportunity for error to creep in. Dust can dim light. Our measurements of star brightness can be off. And here's the kicker. If even one rung of this ladder is miscalibrated, every distance beyond it is wrong. And then we get to type 1, a supernova. These are stellar explosions so consistent in brightness that they became our gold standard for measuring distance to the most distant galaxies. When these stars explode, they reach approximately the same peak brightness every time, making them perfect cosmic mile markers. But here's where it gets juicy. In 2019, a study by Rees and colleagues found something troubling. When they used nearby supernova to calibrate distances using the cosmic distance ladder, and then looked at the most distant supernova, they got a different expansion rate than when they used a cosmic microwave background radiation to calculate it. In other words, two completely independent methods of measuring the universe's expansion rate were giving different answers. This discrepancy is called the Hubble tension, and it's becoming impossible to ignore. Mind-blown moment number 2. The universe might be expanding 10% faster than our models predict. But 10% doesn't sound like much until you realize that 10% of 13.8 billion years is 1.38 billion years. That's not a rounding error. That's like saying you're not sure if your house is 100 years old or 150 years old. Now, here's where James Webb comes in. Its unprecedented sensitivity means it can see Cepheid variables in galaxies that were previously impossible to measure. It can refine our cosmic distance ladder in ways Hubble never could. And every time it does, the discrepancy gets worse, not better. Scientists like Adam Rees at Johns Hopkins University are spending countless hours analyzing this data. And the more they look, the more convinced they become that something fundamental is wrong with our current understanding. Think about this. What if the problem isn't with the observations? What if the problem is with the Big Bang model itself? What if the universe simply isn't 13.8 billion years old? What if we need to push that number back to 26 billion? To 50 billion? The implications are staggering. Let's zoom in on the specific discovery that has Nobel Prize winners concerned. In late 2022 and early 2023, James Webb started releasing images of the most distant galaxies ever observed. The light from these galaxies has been traveling for over 13 billion years to reach us. When we look at them, we're looking back in time to the early universe, just a few 100 million years after the Big Bang. These galaxies should be small. They should be chaotic. They should look like they're still forming. According to our models, galaxies start tiny, just a million or so stars. Over billions of years, they merge and grow through collisions, eventually reaching the massive size of our Milky Way, with its 100 to 400 billion stars. But what James Webb found was fully formed galaxies. Giant, orderly, mature galaxies appearing in an era that should be too young for them to exist. In January 2024, a research team published findings in the Astrophysical Journal Supplement series showing that approximately 6% of the galaxies James Webb detected in the ultra-deep field observations were far too massive and too old to exist according to current models. These aren't borderline cases. Some are off by a factor of 20 to 40. Mind-blown moment number 3. We found galaxies in the baby universe that look like grandparents. Galaxies that, according to our timeline, shouldn't exist for another 10 billion years. Think of it like this. Imagine you're a paleontologist digging through rock layers. You know the oldest layer at the bottom is 65 million years old because of your dating methods. But then you find a perfectly preserved dinosaur skeleton in that oldest layer that looks exactly like dinosaurs that, according to the fossil record, didn't evolve until 60 million years later. Your entire timeline would be wrong. That's what's happening. That's the visceral problem. And here's what's really concerning. Astronomers aren't just finding 1 or 2 anomalies. They're finding them systematically. In January 2023, another team led by Greed et al. Found that galaxies in the early universe are existing at rates 10 to 100 times higher than expected. The predictions are completely off. Now, the scientific community's first instinct was, well, maybe James Webb's calibration is off. Maybe we're misinterpreting the data. So they checked and rechecked and checked again. Multiple independent teams using different analysis methods are getting the same results. The data is solid. So what's the escape route? What explanation could we offer that doesn't require completely restructuring our understanding of the universe? Some scientists suggest that perhaps the early universe had different conditions that allowed galaxies to form much faster. Maybe the laws of physics were slightly different. Maybe dark matter, that mysterious substance that makes up 27% of the universe, behaves differently than we thought. But here's the uncomfortable truth. We don't know. And that's actually the most exciting part of science. When we don't know, we're on the edge of discovery. Let me introduce you to a hypothesis that's gaining serious traction among physicists. And it's absolutely wild. What if the universe is actually much older than 13.8 billion years? Not older by a little bit, older by a lot. In 2022, a controversial paper was published by Gupta titled "The JWST Early Universe May Be in Tension with the Old Expanding Earth Models." It proposed something radical. What if the Big Bang happened further back than we thought, and the universe has been expanding for much longer? Here's how this could work. Remember dark energy? That mysterious force pushing the universe apart faster and faster? What if its strength has varied over time? What if, in the earliest epochs of the universe, it was weaker, allowing gravity to slow the expansion? And only later did it ramp up to the strength we observe today? If that's true, then working backward from our current observations might give us an incorrect age. We'd be assuming a constant expansion rate for the entire history, when in fact it's been changing. Some models suggest the universe could be 26 billion years old. Others, using different assumptions, suggest it could be significantly older. Now, we're not talking about billions or trillions. We're talking about potentially a dramatic overhaul of cosmic chronology. Think of it like this. Imagine you're tracking a car's journey. For the last hour, it's been driving at 60 miles per hour. You assume it's been driving at that speed the entire time. So if you've measured that it's 60 miles away, you assume it left 1 hour ago. But what if it was driving at 30 miles per hour for the first 3 hours, and then sped up to 60? Then it actually left 4 hours ago, not 1. Same current speed, different starting time. Mind-blown moment number 4. We might be off on the age of the universe by a factor of nearly 2. That's not a measurement error. That's a fundamental misunderstanding of cosmic history. And here's what this means. If the universe is significantly older, it changes everything about how we understand the evolution of complexity. Life on Earth? We've been around for about 3.5 billion years. If the universe is 26 billion years old instead of 13.8, suddenly life isn't as rare. It's not as statistically improbable. There's been far more time for it to develop, not just here, but throughout the cosmos. In 2023, physicists including Paul Steinhardt of Princeton and others published work suggesting that cyclic universe models universes that expand and contract repeatedly might be consistent with James Webb observations. These models essentially say the universe might be much older than we thought if we're just in one cycle of an eternal repeating pattern. But here's where we hit the philosophical wall. How do you prove this? How do you test it? The universe doesn't come with a birth certificate. We can only work with light and the remnants of the past. Let me hit you with another piece of evidence that's making cosmologists lose sleep. Stars are made of elements. Our sun is mostly hydrogen and helium, with trace amounts of heavier elements like carbon, oxygen, and iron. We call these heavier elements metals, not in the way you think of metal, but in the astronomical sense. In the early universe, right after the Big Bang, there were no metals. The Big Bang produced only hydrogen, helium, and a tiny bit of lithium. All the heavier elements, the carbon in your body, the iron in your blood, the oxygen you're breathing right now, were created inside stars. When those stars died, they scattered these elements into space. New stars formed from this enriched gas, and this process repeated over billions of years. This means older stars should have fewer metals. Younger stars should have more. It's a cosmic clock built right into the periodic table. Astronomers call this metallicity, and it's a fundamental tool for understanding stellar ages. Here's where it gets weird. Some of the galaxies James Webb is detecting in the early universe have metallicity levels that are far too high for their supposed age. They have heavy elements that shouldn't have had time to be created and distributed throughout the galaxy. Think of it like this. Imagine you find a pristine forest that, according to your records, was planted last year. But you measure the rings in the trees and find some are 100 years old. The forest can't be 1 year old if the trees are 100 years old. A study published in Nature in 2023 by Cameron et al. Found that a galaxy designated GNZ11, which appears to be from about 400 million years after the Big Bang, has stellar populations and metals suggesting an age of several billion years. How can a galaxy that's 13.4 billion light-years away, and thus 13.4 billion years old and look-back time-contained stars that are already several billion years old themselves? The math breaks. It just doesn't work. Mind-blown moment number 5. The chemical composition of distant galaxies is telling us they're older than they should be. We're not just seeing this in their size or structure. We're seeing it in their atomic makeup. This is crucial because it's an independent line of evidence. You can't fake metallicity. You can't misinterpret the spectrum of light in a way that would create a false signal of ancient elements. Either the elements are there, or they're not. And they're there. Some researchers have proposed that perhaps our understanding of stellar nucleosynthesis, the process by which stars create heavy elements, is wrong. Maybe the early universe was incredibly efficient at creating metals, far more efficient than we assumed. But that would require a fundamental overhaul of nuclear physics, something we've tested extensively, both in laboratories and in stars we can observe nearby. We need to talk more deeply about the Hubble constant, because this is the crisis at the heart of everything. This single number, the rate at which the universe is expanding, is fundamental. It's the denominator in the equation that gives us the age of the universe. Get this number wrong, and everything cascades into error. In 2019, Adam Rees and his team published measurements showing that the Hubble constant is approximately 73 kilometers per second per megaparsec. This is higher than predictions from the cosmic microwave background observations, which put it at about 67. Now, you might think, who cares? That's barely different. But cosmology is precision science. A difference of 6 kilometers per second per megaparsec is statistically significant. It's not within the margin of error. It's a genuine discrepancy. Mind-blown moment number 6. 2 completely independent methods of measuring the expansion rate of the universe give different answers, and the difference is too big to ignore. One method is measuring distant supernova and using the cosmic distance ladder. The other is using the cosmic microwave background, the leftover radiation from the Big Bang itself. They should give the same answer. They don't. Think of it like this. Imagine you use 2 different methods to measure the speed of light. Method 1 gives you 299,792 kilometers per second. Method 2 gives you 319,792 kilometers per second. That's a 6.7% difference. Not huge, but huge enough that something is fundamentally wrong with one of your methods or with your understanding of what you're measuring. By 2022, the tension had become worse. Rees and colleagues published new measurements bringing the Hubble constant to approximately 73 kilometers per second, MPC. But the cosmic microwave background observations remained at 67. The discrepancy was now so significant that it couldn't be explained by measurement error alone. Here's what this means. Either our observations are wrong, unlikely, given how many independent methods confirm them, or our models are wrong. And if our models are wrong, then our understanding of the fundamental structure of the universe is wrong. This is called the Hubble tension, and it's not a minor issue in physics. It's a crisis. In March 2024, the astrophysical journal published an extensive review of the Hubble tension, suggesting that it might require new physics beyond our standard model of cosmology. What kind of new physics? Maybe dark energy isn't what we think it is. Maybe there's a new type of particle we haven't discovered. Maybe the universe has additional dimensions we can't see. Maybe gravity operates differently than Einstein theorized on cosmic scales. Every one of these suggestions is revolutionary. Anyone would win a Nobel Prize. But if any of them is true, our framework for understanding reality needs to be rebuilt. Now I want to step back and talk about what physicists are seriously considering as explanations. Because while the crisis is real, so are the possible solutions. And some of them are genuinely mind-bending. First, there's the possibility I mentioned earlier. The universe is simply older. Some models, like those developed by physicists examining cyclic universe hypotheses, suggest the Big Bang isn't the actual beginning. It's just the beginning of our current expansion phase. Before that, there might have been other expansions and contractions, stretching back indefinitely. In this model, the observable universe, the part we can see, is only 13.8 billion years old. But the actual universe has existed forever, cycling through eternal epochs. Second, there's the modified gravity hypothesis. Scientists like Mordechai Milgrom propose theories suggesting that on the largest scales, gravity might behave slightly differently than Einstein's equations predict. If this is true, our measurements of the expansion rate would be off, requiring recalibration of everything. Third, there's early dark energy. Physicists like Rukira Prem and Catherine Zurich have proposed models where dark energy was much stronger in the early universe than it is today. This would have dramatically affected the expansion rate in the primordial cosmos, making the early universe evolve differently than our current models predict. Think of it like this. Imagine you're watching a video of someone aging. For the last 10 years of the video, they've been aging slowly. You assume they've been aging at this slow rate their whole life, so you calculate their age based on that. But what if they aged rapidly when they were younger and have only recently started aging slowly? You've radically underestimated their true age. Fourth, there's the possibility of a modified Big Bang itself. Instead of a singular infinitely hot point, some models suggest the Big Bang was more of a phase transition, a change in the state of reality, rather than a creation from nothing. In these models, the universe might have had a longer history than our current 13.8 billion year estimate. In 2021, Roger Penrose, a Nobel Prize-winning physicist, published a controversial hypothesis called conformal cyclic cosmology, or CCC. He argues that what we think of as the Big Bang is actually the infinite past of another universe. In this model, the entire history of the universe extends infinitely backward. We're not at the beginning of time. We're in one moment of an eternal cosmic cycle. This is radical. This is paradigm shifting. But here's the kicker. Some of the data James Webb is collecting might actually support it. According to Penrose's model, we should see certain patterns in the distribution of ancient galaxies. And some researchers are arguing that James Webb is showing hints of these patterns. Now here's why this matters to you personally. Let me be blunt. If our entire understanding of cosmic history is wrong, if the universe is much older than we thought, if it's infinite, if it's cyclic, that changes your place in the cosmos. You're not living in a 13.8 billion year old universe. You might be living in an eternally ancient universe that's been around forever and will continue forever. Think about that. What does that do to your sense of time? Your sense of meaning? Your sense of urgency? Here's what keeps me up at night about this discovery, and I want to be honest with you. If the universe is older than we thought, if galaxies had more time to develop, if conditions were more stable for longer periods, then the probability of life existing elsewhere in the universe goes way up. Right now, with 13.8 billion years of cosmic history, Earth seems almost impossibly fortunate. Life emerged here about 3.8 billion years ago. Complex life took a while to develop. Intelligent life has only appeared in the last 200,000 years. In the vast cosmic timeline, we're the very last thing to emerge, and our existence seems almost like a fluke. But if the universe is 26 billion years old, or older, if other solar systems had 5, 10, or even 15 billion years before Earth even existed, then the development of life elsewhere becomes less of a fluke and more of an inevitability. Mind-blown moment. The universe might be absolutely teeming with life, not because we've discovered alien signals, but because the timeline is now long enough that it makes mathematical sense for life to have emerged multiple times, independently, across the cosmos. This connects to something called the Fermi paradox, articulated by physicist Enrico Fermi in 1950. He asked a simple question: where is everybody? If the universe is so old and so large, and if life can develop, why haven't we detected any alien civilizations? Why haven't they contacted us? Part of the answer might be, they had more time than we thought. And if they had more time, they might have risen and fallen, achieved technological singularities, and collapsed into chaos, explored the galaxy, and then withdrawn. By the time we become technologically advanced enough to detect them, they might already be gone. Or, and this is darker, they might still be out there, and they might be watching us. A civilization that emerged 10 billion years before us would be so vastly more advanced than we are that we wouldn't even recognize them as technology. We'd mistake them for natural phenomena. They'd be gods to us. Think about what you knew about technology 100 years ago. Then think about what exists now. A civilization 10 billion years more advanced than us? We can't even conceptualize that difference. But here's the hopeful part, and this is crucial. The fact that we're here, that we've developed consciousness, that we're capable of understanding the universe. That becomes even more remarkable if the universe is older, because it means that against all odds, against billions of years of cosmic possibility, the exact right conditions came together to create you, to create awareness, to create the capacity to wonder. Let me paint a picture of what happens if this goes beyond hypothesis and becomes accepted science. Imagine a scientific conference in 2026 or 2027. A researcher stands up and presents data so compelling that the astronomical community can no longer deny it. The age of the universe needs to be revised, not by a little, significantly. What happens next is the interesting part. Because when one foundational assumption of science becomes untrue, you have to question everything that built on top of it. It's like discovering the ground floor of a skyscraper was built on faulty calculations. You don't just fix the first floor. You have to inspect every floor above it. Suddenly, cosmological models that seemed impossible become plausible. The singularity at the Big Bang, the infinitely hot, infinitely dense point, might not have been as singular or extreme as we thought. The physics governing the early universe might be more closely related to the physics we observe today, making it less alien and more comprehensible. Here's what a Nobel Prize winner like Paul Steinhardt might say in this scenario, and he's one of the physicists seriously considering these ideas. We built our entire framework assuming a specific age for the universe. Every prediction, every model, every hypothesis about the early cosmos was informed by that number. If that number is wrong, we need to reconsider everything. And that's terrifying and exhilarating, because it means we're not done discovering the universe. We're not even close. Mind-blown moment 7. The discovery that we've been wrong about the universe's age doesn't mean we failed. It means we're on the cusp of understanding the universe more deeply than we ever have before. Think of it like this. A detective builds a case based on evidence suggesting the crime happened at midnight. They construct an entire timeline around this assumption. But then new evidence emerges suggesting the crime actually happened at 6 p.m. Suddenly, every witness statement, every piece of evidence, every assumption needs to be re-examined. It's not that the detective failed. It's that they've discovered a deeper truth. This is where cosmology is right now. We're in the phase where the evidence is mounting, but the implications are so massive that the scientific community is proceeding carefully. But they're proceeding. And with each new observation from James Webb, the evidence gets stronger. Let me bring all of this together, because here's what's remarkable. Every piece of evidence I've shown you points to the same conclusion. Something fundamental about our understanding of the universe is shifted. It's not just about age. It's about everything that age implies. The distant galaxies that are too big, the metallicity that's too high, the expansion rate that doesn't match up, the supernova measurements that disagree with radiation measurements. These aren't coincidences. They're not random noise in the data. They're all pointing to the same truth. And that truth is this: we need a new cosmic model, not a tweaking of the old one, a new framework. In 2023, physicist Margan from the University of Washington said something in an interview that stuck with me. He said, "We're entering a new era where our assumptions about the universe are being tested more rigorously than ever before. And we're finding that some of those assumptions are wobbling." Wobbling. That's the perfect word. Our cosmic model is wobbling. And the more precise our instruments become, the more pronounced the wobble gets. Think back to when Copernicus suggested the Sun, not Earth, was at the center of the solar system. The Church rejected it. Scientists were skeptical, but the evidence accumulated. The observations couldn't be denied. And eventually, reality won out over assumption. We're in a similar moment right now. Except now, we have telescopes that can see light from over 13 billion years ago. We have computers that can process data in seconds that would have taken physicists decades to calculate. We have the tools to confront reality directly. And reality is saying, "You've been thinking about me wrong." Here's the most mind-blown moment of all. The universe is stranger than we've given it credit for. It's older, or it's cycling, or it's operating under rules we don't fully understand. And that strangeness is beautiful, because it means we haven't figured it all out. It means there's still mystery. There's still discovery waiting. In 2024, articles about the crisis in cosmology filled scientific journals. Nature published an extensive piece on the challenges facing current models. The Scientific American ran headlines about paradigm shifts. And every one of these pieces pointed back to the same source. James Webb is seeing a different universe than we expected. Now I want to talk about what this means for you. Not as a scientific abstraction, but as a human being living in this universe. You are made of stardust. The carbon in your body, the calcium in your bones, the iron in your blood, all of it was forged in the cores of stars that died billions of years ago. When those stars exploded, they scattered these elements across space. They drifted for millions of years. They coalesced into new stars, new planets, and eventually, through an improbable series of chemical reactions, they became you. Think about that for a moment. You are literally made of the universe. You're not separate from it. You're a part of it that became conscious. You're the universe learning about itself. Now, if that universe is older than we thought, if it has been around for 26 billion years instead of 13.8, what does that change? It means the journey from Big Bang to you took even longer. It means there were more moments, more possibilities, more incredible chances for something to go wrong and end your entire existence before you got here. But here you are, conscious, reading this, understanding that you are, in a very real sense, one of the universe's greatest achievements. When you wake up tomorrow morning and you're stressed about your job, or your relationships, or your health, remember this. The universe spent billions of years, possibly over 26 billion years, arranging the atoms that make up your body. It spent millions of years getting the conditions right on Earth for life to emerge. It spent hundreds of thousands of years developing the neurological complexity that allows you to think, to feel, to wonder. You're not insignificant. You're not an accident. You're the deliberate culmination of cosmic history. And here's something even more profound. You're a part of the process by which the universe understands itself. Every time you learn something, every time you wonder about the cosmos, every time you push the boundaries of human knowledge, you're extending the universe's self-awareness. You're participating in the process of cosmic discovery. The scientists at the Space Telescope Science Institute analyzing James Webb data are doing something remarkable. They're using the matter that's arranged in their brains to understand the matter arranged in distant galaxies. They're closing a loop of understanding that began billions of years ago. And you, by engaging with this information, by thinking about it, by questioning it, and wondering about it, you're doing the same thing. You're participating in humanity's greatest endeavor, understanding the cosmos from which we emerged. So what happens next? What's the next frontier in this cosmic investigation? First, more data from James Webb. The telescope has been in space for just over 3 years at the time of writing, and it's designed to operate for at least 10 years. It's going to continue peering deeper into the early universe, getting more precise measurements, finding more anomalies, or confirming the pattern we're already seeing. Second, new missions are being developed. The Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will be designed specifically to measure the expansion rate of the universe with unprecedented precision. It will help resolve the Hubble tension. If current models are wrong, Roman will help us understand why. Third, ground-based telescopes are improving. The extremely large telescope in Chile, set to come online soon, will have a mere 39 meters in diameter, more than twice the aperture of current ground-based telescopes. It will allow astronomers to observe distant galaxies in even greater detail than James Webb can from space. Mind-blown moment 8. The next generation of telescopes being built right now will make James Webb look primitive, and they'll be used to investigate the questions that James Webb has raised. Think of it like this. James Webb gave us a glimpse of the basement of the universe. The next generation of telescopes is going to give us a tour of every room. They're going to map out the early universe in stunning detail. And in doing so, they might just rewrite the history books. But beyond just building bigger telescopes, there's theoretical work to be done. Physicists like Lisa Randall at Harvard, Juan Maldacena at the Institute for Advanced Study, and others are developing new models. Models that might incorporate dark energy as a fundamental force rather than a mysterious constant. Models that might allow for cyclic universes. Models that might introduce extra dimensions. Some of this work is highly speculative, but that's where all great science starts. In 1905, Einstein's theories of special relativity seemed purely speculative. Now they're confirmed experimentally thousands of times a day. Ideas that sound impossible today become tomorrow's foundation of knowledge. Here's the beautiful thing. We're in the middle of that process right now. We don't know where this goes. The universe is keeping its secrets, but we're getting better at asking questions. And every answer leads to new, deeper questions. Let me bring this home. Let me tell you what I believe is happening at the deepest level. We're living through a revolution. Not the kind with barricades and conflict, but the kind where reality itself is being reconsidered. A Nobel Prize winner said, "It's a different universe than we thought," and he was right. But not because the universe changed, because our understanding of it is changing. James Webb Space Telescope is showing us that the universe is stranger than we imagined. It's older, or it's different, or it's operating under rules we haven't yet formulated. It's more beautiful and more complex than our current models can contain. And that's not a problem. That's an invitation. Every great scientist, every great thinker, has been someone who looked at the world and said, "I don't think we understand this yet. Let me investigate." Henrietta Leavitt didn't have a PhD, but she developed the cosmic distance scale. Saul Perlmutter, Adam Rees, and Brian Schmidt discovered dark energy because they were willing to question assumptions. Roger Penrose developed conformal cyclic cosmology because he dared to imagine the universe might be fundamentally different than we thought. And now, in this moment, we're inviting you to participate in that same process. Not as a passive observer, but as an active thinker. Look at what James Webb is showing us. Think about what it means. Question the old models. Imagine new possibilities. Here's what happens if you do that. You stop being a spectator in the universe and become a participant. You become part of the community of people asking the deepest questions about reality. You join Henrietta Leavitt, Saul Perlmutter, Roger Penrose, and everyone who has ever wondered about the cosmos and dared to seek answers. The universe James Webb is revealing the one that's older, stranger, more beautiful than we expected. That's your universe. You live in it. You're made of it. And your participation in understanding it matters. Let me be direct. If you've made it this far in the video, you're exactly the kind of person who changes the world. Someone who cares about understanding. Someone who's willing to grapple with complexity. Someone who recognizes that reality is more profound than we usually give it credit for. I'm asking you to do 4 things. First, subscribe to this channel. Not for me, but for yourself. Keep learning. Keep questioning. Keep participating in this journey of discovery. The algorithm makes it hard for educational content to reach people, and every subscription helps us reach one more person who's hungry for truth. Second, comment below. Tell me what mind-blown moment hit you the hardest. Tell me what you think about the age of the universe. Tell me whether you believe we're going to have to fundamentally revise cosmology. I read every comment, and I engage with as many as I can. This is a conversation, not a lecture. Third, share this with someone. If you know someone who loves science, who wonders about the cosmos, who's curious about how reality works, share this video with them. Educational content thrives when people share it. You become part of the discovery process when you bring others into it. Fourth, and this is the most important, look up at the night sky. Find a clear night, get away from light pollution if you can, and just look at the stars. Remember that light from some of those stars has been traveling for longer than we thought. That some of those photons have journeyed longer through the cosmos than we realized. That you're looking back in time to an early universe that was apparently nothing like what our models predicted. Feel the wonder of that. Hold on to it. Let it change you. Because wonder is what drives science. Wonder is what drove Copernicus to question the geocentric model. Wonder is what drove Einstein to reimagine space and time. Wonder is what drove the teams at the Space Telescope Science Institute to build James Webb and point it at the stars. And wonder is what's going to drive the next revolution in our understanding of the universe. That revolution might start with you. The Nobel Prize winner who said, "It's a different universe than we thought." He was speaking to the scientific community. But I'm telling you, he was speaking to all of us. Every person who has ever looked at the night sky and wondered. Every person who has ever asked why and how. Every person who refuses to accept that we've figured it all out. The universe is inviting us to grow, to question, to discover, to become more than we are. And maybe, just maybe, that's the real difference. Not that the universe is different than we thought, but that we're becoming different through understanding it. We're evolving intellectually. We're becoming more conscious. We're becoming more truly human. That's the revolution. That's what James Webb is really showing us. And you're part of it now. Thank you for being here. Thank you for caring about truth. Thank you for wondering about the cosmos. In a world full of distractions and easy answers, your presence here, your willingness to grapple with complexity and mystery matters. Go look at those stars. Go ask those questions. Go change the world. The universe is waiting. I need to take us deeper into one of the most important pieces of evidence in all of cosmology. And it's something that might seem obscure, but it's absolutely crucial to understanding why scientists are so concerned about James Webb's discoveries. In 1965, two physicists named Arno Penzias and Robert Wilson were working with a radio antenna at Bell Labs. They kept detecting this annoying background noise that wouldn't go away, no matter what they did. They thought it was pigeon droppings interfering with their equipment, so they cleaned it. The noise remained. What they had actually discovered was the cosmic microwave background radiation, or CMB. This is literally leftover radiation from the Big Bang itself. It's the oldest light in the universe, and it won them the Nobel Prize in Physics in 1978. Think of it like this. Imagine the universe immediately after the Big Bang was like the inside of a furnace, incredibly hot, filled with radiation. As the universe expanded, it cooled down, just like a room cools when you open all the windows. Eventually, about 380,000 years after the Big Bang, it cooled enough that electrons and protons could combine to form neutral atoms. Light could finally travel freely instead of being constantly scattered. That light, that first light, has been traveling through the universe ever since. We detect it today as the CMB, and here's why it's so important. The CMB is like a fossil record of the early universe. Its temperature, its variations, its polarization, all of these contain information about what the universe was like in its infancy. When we map the CMB precisely, we're reading the baby picture of the cosmos. In 2009, the Planck satellite launched. It was designed to map the CMB with unprecedented precision, and it succeeded. It gave us the most detailed map of the early universe we've ever had. From this data, combined with observations of galaxies and supernova, physicists calculated that the universe was 13.8 billion years old, plus or minus 37 million years. That's incredibly precise. We know the age of the universe to within 0.003%. But here's the problem. That age is based on assumptions about how the universe has expanded. The Planck satellite assumes a specific model of the universe called the lambda cold dark matter model, or CDM. This model assumes that the universe is flat, that dark energy is constant throughout time, that dark matter behaves in specific ways. And if any of those assumptions is wrong, the age calculation is wrong. Mind-blown moment 9. The entire foundation of our age estimate for the universe rests on assumptions that we've never directly tested. We're not measuring the age directly. We're measuring expansion rate and then calculating backward, assuming certain physical laws applied in the early universe. When James Webb started detecting galaxies that were too old, too large, and too metal-rich for the 13.8 billion year timeline, it raised a crucial question. What if one of those assumptions is wrong? This is where it gets really interesting. Some physicists have proposed that early dark energy that was much stronger in the early universe than it is today could change the entire calculation. If dark energy was stronger when the universe was young, it would have pushed the expansion faster, which would change how we calculate age from current observations. A team led by Vivian Poulin at the University of Montpellier published research in 2019 suggesting that early dark energy could solve multiple problems in cosmology simultaneously. It could address the Hubble tension. It could explain why galaxies formed faster than we expected. It could reconcile observations that currently seem contradictory. But early dark energy isn't just another tweak to the model. It's a fundamental change to how we understand the dominant form of matter in the universe. It would require new physics, new particles, new fields we haven't discovered yet. Think of it like this. Imagine you're analyzing a building structure. You measure the weight distribution and calculate that it should take 100 years to develop cracks. But you observe cracks appearing after only 50 years. You could blame faulty materials, or you could ask, what if there was an additional weight I didn't account for during the first half of the building's existence? Something that disappeared over time? That's what early dark energy proposes for the universe. A mysterious force that was present in the early cosmos, but has since diminished or disappeared. The profound implication: the universe has a history more complex than we thought. It wasn't just expanding steadily. It was actively evolving. The rules governing it changed over time. Here's something that will absolutely blow your mind. We don't understand what 95% of the universe is made of. 5% is regular matter atoms, stars, galaxies, you, me, everything we can see and touch. But the other 95%? We have no idea what it actually is. 27% is dark matter. It doesn't emit light. It doesn't reflect light. It doesn't interact with light in any way we can detect. We know it's there only because of its gravitational effects. We know it exists because galaxies rotate too fast. If they were only made of the visible matter we can see, they would fly apart. Something invisible is holding them together through gravity. We call that something dark matter. And 68% is dark energy. It's the force pushing the universe apart, faster and faster. We don't know what it is either. We just know it's there because distant supernovae are farther away than they should be. So we're living in a universe that is almost entirely made of stuff we don't understand. And one of the profound problems that James Webb's discoveries are raising is this. What if our assumptions about dark matter are wrong too? Here's the connection. If galaxies in the early universe are too large, too massive, and too well developed, one explanation is that there's more dark matter than we thought. Dark matter would provide additional gravity that could hold these massive galaxies together. It would allow them to retain the gas they need to form stars rapidly. But here's the problem. Our models of dark matter are based on assumptions. We think dark matter is made of WIMPs, weakly interacting massive particles, or axions, or sterile neutrinos, or some other exotic particle we haven't detected. But what if we're wrong about what dark matter is? What if dark matter itself evolved over time? What if it behaves differently in the early universe than it does now? A physicist named Mordechai Milgram proposed something radical called modified Newtonian dynamics, or MOND. He suggested that instead of invoking dark matter, maybe gravity itself works differently at very large scales. Maybe Newton's laws need to be modified. If MOND is correct, then our entire understanding of how galaxies work would need to be overhauled. And it would change how we interpret James Webb's observations. Instead of asking, why are these galaxies too massive? We ask, why does our model of gravity predict differently than what we observe? Think of it like this. Imagine you're watching a tightrope walker on a rope you can see. They're moving across it at a certain speed. You calculate that based on the rope's tension, they should be moving slower. So you conclude there must be an invisible force helping them along. You call it invisible helper particles. But what if the problem isn't an invisible helper? What if the rope is under more tension than you measured? What if the physics of the rope itself is different than you assumed? Mind-blown moment 10. Everything we think we know about dark matter and gravity might be based on incorrect assumptions about how the universe works at cosmic scales. In 2023, a study by McGall and Lely provided evidence supporting modified gravity theories, showing that galaxy rotation curves follow patterns that are difficult to explain with traditional dark matter models, but more consistent with modified gravity. But here's what's crucial. We don't have a complete, testable theory of modified gravity yet. MOND works for some observations, but fails for others. And yet, the failures of our dark matter models are becoming harder to ignore. We're in a situation when neither our dark matter hypothesis nor the modified gravity hypothesis is fully satisfactory. And that's actually exciting, because it means there's a deeper truth waiting to be discovered. When our models fail to explain observations, we're on the verge of breakthrough. The implications are staggering. The invisible infrastructure of the universe, the dark matter and dark energy that make up 95% of everything might operate under completely different rules than we've assumed. And if that's true, then the early universe, where these effects were even more pronounced, might have been radically different from what we've been modeling. Let me walk you through what our models say should happen when you're forming the very first stars and galaxies in the universe. Immediately after the Big Bang, the universe was a sea of hydrogen, helium, and lithium. Gravity was pulling these gases together into denser regions. After about 100 million years, the first stars ignited. These were population 3 stars, the first generation. These earliest stars would have been massive. And when they burned out, and they burned out quickly because massive stars have short lifespans, they exploded as supernova, scattering the heavy elements they created throughout space. According to our models, this process would take billions of years. You'd start with small, simple galaxies. They'd collide and merge. Slowly, over eons, they'd grow larger and more complex. It's a bottom-up process, small things combining into bigger things. But James Webb is showing us something different. It's showing us massive, complex galaxies existing when there's barely been time for even a few generations of stars to have lived and died. So either, 1, the early universe was far more conducive to rapid star formation than we thought. 2, stars formed faster than our stellar evolution models predict. 3, galaxies assembled faster than our merger models suggest. Or 4, some combination of all 3, indicating our understanding of stellar and galactic physics in the early universe is fundamentally incomplete. A team led by Jung et al., publishing in Nature Astronomy in 2023, found evidence that star formation in the early universe might be 10 to 100 times more efficient than current models predict. They studied a distant galaxy and found evidence of rapid, vigorous star formation that shouldn't be possible according to standard models. Mind-blown moment 11. The physics of how stars form might be completely different in the early universe than it is today. Think about it like this. Imagine a recipe for baking bread that takes 3 hours. You carefully follow all the steps. But one day, you notice someone producing perfectly baked bread in 30 minutes using the same recipe. That doesn't make sense. Either they're using different techniques, different ingredients, or the recipe works differently under certain conditions. That's what's happening with star formation. We have our recipe for how galaxies form, but the early universe seems to be producing fully formed galaxies much faster than our recipe allows. One possibility that physicists are seriously considering: the early universe had conditions that amplified star formation. Maybe the gas was denser. Maybe it was cooler. Maybe gravity was operating with more efficiency. Maybe the first stars were different from what we've modeled. Or here's a wild possibility. What if supermassive black holes in the early universe were far more common than we thought? Supermassive black holes at the centers of galaxies can actually regulate star formation through feedback mechanisms. If there were more of them, and they were more active, they could have dramatically changed how galaxies developed. In 2023, James Webb detected supermassive black holes in the early universe that appear to be far more massive than they should be. Some of these black holes are billions of solar masses in galaxies that shouldn't have had time to develop black holes that large. This is the black hole problem, and it's closely related to the galaxy problem. If galaxies formed faster, and if supermassive black holes at their centers grew faster, then we need to completely revise our understanding of how these cosmic objects develop and interact. Here's the beautiful thing about science. When our models start failing, when we find things that don't fit, that's when we get to build something new. That's when we get to develop better understanding. Let me take a step back and talk about something deeper. The history of the universe is a history of increasing complexity. This is one of the most profound patterns in nature. Right after the Big Bang, simplicity, just energy and the most basic particles. After 100 million years, the first stars ignite. Complexity is increasing. After a few billion years, galaxies are colliding and merging. Structure is growing more elaborate. After 4.5 billion years, our solar system forms. Further complexity. After 3.8 billion years of Earth existing, life emerges. Suddenly, we have self-replicating systems. organization at a completely new level. After another 3.5 billion years, consciousness emerges. Life becomes aware of itself. This progression from simplicity to complexity to consciousness is the story of the universe. And it's been happening in this specific sequence for what we thought was a specific amount of time. But if the universe is older than we thought, this timeline stretches. This means there was more time for complexity to build, more time for consciousness to emerge elsewhere, more time for the universe to develop meaning and self-awareness. In physics, there's a concept called the arrow of time. It describes why the past is different from the future, why we remember the past but not the future, why entropy increases. The arrow of time is fundamentally connected to the increase in complexity and the emergence of consciousness that observes and measures time. Some physicists, including Roger Penrose, have suggested that consciousness itself might be fundamental to the universe, that the universe's purpose is to become aware of itself, that we as conscious beings are the universe achieving self-awareness. If that's true, then discovering that the universe is older than we thought takes on profound significance. It means the universe has had longer to develop consciousness. It means we're not some accident in a young cosmos, but the product of a vastly ancient and purposeful process. Mind-blown moment 12. We might live in a universe whose entire purpose is to become conscious. And we're that consciousness. The universe achieved self-awareness through you. Now let's talk about something that's both mind-blowing and somewhat controversial, the multiverse. If our universe is older than we thought, or if it operates under different rules, one implication is that there might be other universes. Multiple universes, perhaps infinite universes, each with its own physical laws, its own history, its own possibilities. This isn't just speculation. It comes from serious physics. First, there's the inflationary multiverse. Alan Guth and Andre Linde developed inflation theory, which suggests the Big Bang was preceded by a period of exponential expansion. But here's the thing. Inflation might not have stopped everywhere simultaneously. In some regions, it might continue eternally. In others, it might have stopped, creating pocket universes, separate bubbles of space-time with their own properties. If this is true, then our Big Bang wasn't the beginning of everything. It was just the beginning of our particular pocket universe. And there might be infinite other pocket universes, each with its own timeline, its own physical laws. Second, there's the quantum many-worlds interpretation. Every time a quantum event has multiple possible outcomes, the universe splits into multiple branches, one for each possibility. You're not alone. In another universe, right now, another version of you is reading a slightly different version of this paragraph. And another. And another. Infinite versions. Infinite possibilities. Third, there's the mathematical multiverse proposed by physicist Max Tegmark. He suggests that every logically consistent mathematical structure that could possibly exist does exist as a universe somewhere in the multiverse. All possible universes exist. All possible physical laws. All possible histories. If any of these ideas is correct, then the age of our particular universe becomes less important. We're just one universe among infinite others. The question shifts from how old is the universe to in what multiverse do we exist? And here's where it connects to James Webb's discoveries. If there are multiple universes with different laws and different histories, then maybe what seems like a contradiction in our universe galaxies that are too old, expansion rates that don't match up, is actually normal. Maybe universes with different characteristics look like this. Maybe other universes look completely different. We might be that ant. We might be measuring only our universe and assuming those measurements apply to all of reality. In 2022, physicist Andre Linde gave a lecture at Stanford about the infinite multiverse and the implications for understanding our cosmos. He said, "The universe is so big and so old and so varied that within it, every possible thing that can happen does happen, infinite times. This changes how we think about probability, about destiny, about ourselves. Mind-blown moment 13. There might be infinite universes, each with its own history, its own age, its own physics. And we happen to live in one of them. Here's where we enter the deepest, most controversial territory. And I'm going to present this carefully because it touches on both physics and philosophy. In quantum mechanics, there's a phenomenon called the observer effect. At the quantum scale, the act of observing something changes its properties. Before you measure an electron, it exists in a state of superposition. It's in multiple states simultaneously. The moment you measure it, it collapses into one state. For decades, physicists have debated what this means. Does observation require a conscious observer? Does consciousness create reality? Most physicists avoid this interpretation. They prefer to think of observation as any kind of interaction or measurement, whether conscious or not. But some serious physicists take the consciousness interpretation seriously. John von Neumann, one of the founders of quantum mechanics, proposed that consciousness is fundamental to collapsing the wave function. Eugene Wigner expanded on this, suggesting that the universe exists in a superposition of states until a conscious being observes it. Now, what does this have to do with James Webb and the age of the universe? Here's the connection. If consciousness is fundamental to reality, if our observation of the universe shapes it, then the universe's history is not independent of observers. The universe exists in a specific state because we're observing it in a specific way. And if that's true, then the question, how old is the universe, might not have a single answer independent of who's asking. The universe might be 13.8 billion years old to some observers and 26 billion years old to others, depending on how their observation wave function collapses. This sounds crazy, but it's not fringe science. It's a serious interpretation of quantum mechanics held by some serious physicists. In 2021, physicist Henry Stapp published works suggesting that consciousness plays a causal role in the physical world. He argued that quantum mechanics requires consciousness to explain how wave functions collapse and how reality becomes actualized. If this is true, then James Webb isn't just discovering the universe's age, it's creating it. It's actualizing one specific history out of infinite possibilities. Mind-blown moment 14. Your observation of the universe might be literally creating its properties. You're not discovering reality. You're creating it through the act of observation. Now, I know this sounds wild, and it is, but it's consistent with some interpretations of quantum mechanics. And it raises a profound question. If consciousness creates reality, what's the significance of your consciousness? What's the significance of your observation? It means you're not separate from the universe. You're not a spectator. You're a participant in creating it. So where does cosmology go from here? How do we reconcile these contradictions? How do we build a better model? The answer is, we don't know yet. And that's the exciting part. But we can see the direction science is moving. There's a growing consensus that the standard model of cosmology, the lambda cold dark matter model that served us well for 30 years, needs significant revision. Some physicists are proposing modifications to dark energy. Others are suggesting modified gravity. Still others are exploring entirely new frameworks that incorporate quantum mechanics and gravity. Together, something called quantum gravity or quantum cosmology. One of the most promising approaches is called loop quantum gravity. It suggests that space and time aren't continuous. Instead, they're quantized, made of discrete loops at the smallest scales. If space and time are quantized, then the Big Bang might not be a true singularity. There might be a bounce point before the Big Bang where the universe was contracting, then expanded. If there was a bounce, then the universe could be infinitely old. It could have existed forever, bouncing between contractions and expansions. This is similar to Penrose's conformal cyclic cosmology. Another promising approach is string theory and its various offshoots. String theory suggests that fundamental particles aren't point-like, but are tiny vibrating strings. Different vibrational modes create different particles, and different configurations of strings create different physical laws. If string theory is correct, then our universe might be one of 10,500 possible configurations. That's a 1 followed by 500 zeros. Each configuration would have different physical laws, different constants, different history. In 2024, physicist Juan Maldacena at Princeton published work suggesting that the holographic principle, the idea that our three-dimensional universe is a projection of information on a two-dimensional surface, might reconcile quantum mechanics with general relativity, and might explain why galaxies formed faster in the early universe than our models predict. The exciting thing, we're in the middle of this research. These ideas are being tested. James Webb is providing data that's either confirming or refuting these theories. In the next 5 to 10 years, we should have much clearer answers. We might discover that the universe is older than 13.8 billion years. We might discover new particles. We might discover that space-time itself has a structure we never imagined. We might discover evidence of other universes, of consciousness affecting reality, of the universe having purpose and direction. Or we might discover that our current models are actually correct, and there's a subtle explanation for why galaxies formed faster that we simply hadn't thought of. Either way, science wins, because science is the process of questioning, testing, and refining our understanding. Every discovery, even when it contradicts previous beliefs, is progress, and you get to be part of this. Every time you learn something new about the cosmos, every time you question an assumption, every time you wonder about the universe, you're participating in humanity's greatest adventure. Thank you for taking this journey with me